one, you know, we don't have a product, we don't have a starting material. What I'm adding is water and acid, and what's happening, right? And what's happening is I'm ending up with the alcohol and the carbonyl. So over here, what I had was the acetal, right? So I've got that acetal species. Well, if I look at the bottom, all that is the reverse of the top. And there I'm making this diacetal, or this acetal, right? So there's several things through the carboxylic, the aldehydes and aldehydes and ketones, as well as the carboxylic acid derivatives that are going to be reversible. Okay, and I'll go through a few of those today, right here at the beginning from aldehydes and ketones, because it looks like you're kind of missing some of those. And often we refer to them as hydrolysis, because the idea is that if you add water, you can get the reaction to work, go backward. So if we think about these two reactions, if I add an excess of water, I'm going to go back to the ketone and I'm going to kick off the ethanol. If I add an excess of ethanol, more or less under the same conditions, then I'm going to lose water, right? Because what have I lost over here? What I've lost is water, right? So depending on whether I add an alcohol, I can go forward to the acetal, right, and remove water. Or if I add water, I can remove the ethanol and go back to the ketone, okay? So there's several of these types of processes that go back and forth. The acetal-ketal formation, that's reversible. We also have the imine. So if I take and I add a carbonyl, you know, with an NH2, CH3, right, and I add some acid, right, what I'll get is the imine. But if I take the imine and again, what we don't usually show is the byproduct. What I've removed now is water, right? So water is what's being lost. So if I start with the imine and now add water and acid, what's going to happen? Well, now I'm going to reverse that. I'm going to go back to the carbonyl, right? And I'm going to be kicking off the ammonium, right? So I'm going to end up going back the other way. This would work the same with an enamine. So if I have the aldehyde and I react that with a nitrogen with 2 methyl groups on it, right, a little bit of acid, that will go forward, right, to the enamine, which is this species, right? You got the amine and you got the double bond. So ene, double bond, amine, enamine. But if I take an enamine, right, and add acid and water, I'll just reverse that and go back to the ketone, the aldehyde. Okay. So I can drive these reactions one way or the other. I drive them by changing the concentrations. The conditions are often the same, right? It's just acid promoted. The other one that we saw in that chapter was the thiols, right? I could take this aldehyde, react it with this sulfur, right? TSOH, or actually it should be big T, little o. I mean, big T, little s, big O, okay? And this is gonna make that thioketal, that cyclic thioketal. Okay. And now what is the carbon that I wanna watch for if I was gonna reverse this? Well, it's one where my 2 nitrogens are, my 2 sulfurs attached. Up here on the enamine, it's where the nitrogen was attached. Up here on the imine, it's where the nitrogen was double bonded. On the acetal, it's where the 2 oxygens, right? So when you have 2 bonds to a more electronegative atom, that's when I reverse it, that's where I'm going to put my acid. So if I look at this one backwards, where I want to focus, right, is that position right there. That's going to be the position that if I took this with water and some acid, right, and toluene sulfonic acid works fine, I'm going to get the carbonyl, okay? So I had several people had issues with this. So again, these, if we went over the mechanisms quite a bit, lots of times, right? And what the mechanism is it's reversible. So you can drive the reaction forward with one reagent, you can drive that reaction backwards with another reagent. Yes, ma'am. Right, but if you looked at that molecule, and I'm not sure if exactly here, you had an alcohol on one side. Okay, so you had alcohol on one side and the aldehyde will work the same way, and I've got the aldehyde. Well, if I add the TSOH, all I'm doing is adding the acid, right? So therefore this is going to do that reaction, 1, 2, 3, 4, 5, 6. And I think it was a 5-membered ring in that problem, right? I'm gonna end up with this, right? So what I'm forming, right, is the hemiacetal, but just like this reaction up here, right? I have an alcohol and a carbonyl. We'll make it a little bit generic, right? And an acid. And what that problem had was an alcohol, a carbonyl, and an acid, right? It was just that the carbonyl and the alcohol were in the same molecule, which then forms this cyclization, okay? Yes, ma'am. Yeah, so what we're looking at is that this, and I'm gonna change colors, this is attacking that. So if we put 1, 2, 3, 4, 5, 6, then here's where it was attacked, right? 1, 2, 3, 4, 5, 6, right? And then of course you're breaking this bond too. That's why it's single bond oxygen. Okay. And if we color coded our oxygens, you know, this would be the hot pink, right? That's the hot pink. And then let's pick another yellow you won't see. This highlighted green, right? That's this. So your alcohol becomes in the ring in this case, right? And your carbonyl becomes the OH on the outside. Okay. So I did give you a couple more days. So you got till Thursday to do that homework assignment. I'm going to be putting up carboxylic acids. Again, I'm probably going to give you more than just a week. I'm going to try and get that up this afternoon. Or, you know me, maybe tomorrow morning. And when you're looking at it, right, one of the things you want to think about is start early, because there's going to be lots of problems. I'm giving you lots of problems because I want you to get lots of practice, right? But just like these, right, I saw 3 different problems that really all had to do with this back and forth, right? This back and forth. Okay. All right, let's go ahead and move on into the rest of the carboxylic acid chapter. So we looked at reactivity. So now let's look at the base reaction that we're going to be dealing with for the rest of the chapter, most of the chapter, nucleophilic acyl substitution. And we're going to do it generic, and then I'll give you an example of another one. So if we take a carboxylic acid or carboxylic acid derivative, right, react that with a nucleophile, what I'm going to get is substitution. If you remember aldehydes and ketones, right, they did nucleophilic addition reactions. So in that case, we had the R and then the you know, R prime with the carbonyl. Here, when we edit our nucleophile, you know, we did a addition. The main difference between here is that if we look at our Z is going to be, in the case of hydroxylic acid, right, would be OH, chloride, the anhydride, and all of these are pretty well decent leaving groups, right? Now the nitrogen negative is a little bit less, but we can see how having a negative charge on all of those is not going to upset our stomach much. We've seen this, right? A chloride negative, no problem. But when we look at aldehydes and ketones, now we're talking about a hydrogen negative or a carbon negative, right? So an aldehyde would be a hydrogen negative leaving. How likely is a hydrogen negative going to leave? Not, right? The pKa of that hydrogen is 60, right? So that's very unstable, right? The pKa of a methanol alkane is going to be around 50, right? So we're talking about unstable. So these are not going to leave. But when we look at this group, right, we can say they are very stable to decently stable. And, you know, that means that we've got great leaving groups to okay leaving groups, right? So with that carboxylic acid derivatives, now we have possible leaving groups. That's why we get substitution versus addition. So let's look at the mechanism. Again, let's look at it generically. So if I have my Z on here, it can be anything. First thing happens, the nucleophile attacks electrophile, leaving group leaves. I get the tetrahedral intermediate. Okay, this is important. So it's not a concerted mechanism. Then this can come down and kick off the Z. Could it have come down and kicked off the nucleophile? Yes. So therefore that back reaction is also possible. And then this gives me now the nucleophile substituted plus the Z. So if we look at this reaction, that means that what I'm really going to be comparing to know whether these reactions are going to occur is I've got an equilibrium process here. And what I'm going to be comparing right, is the nucleophile to the leaving group, the Z. And what we looked at on Thursday was that our chlorine, right, is a better leaving group than our anhydride. And we can get this all from the pKa's of the conjugate acids, which then goes down to our methoxides, which is about the same as our hydroxides, right? So our methyls and our hydroxyl are the same, and then that's going to be better than our amides. Which just kind of sets up a cascade. That means that the chloride could be substituted to make the anhydride. The anhydride could be substituted to make the, the ester, and the ester and the carboxylic acid are about the same. And then those could potentially make the amide, right? So if that's confusing you, let's put it this way. This one could be substituted directly to make the anhydride. The anhydride could be substituted to make the ester. The ester and the acid could be interconverted, right? And then the acid could be turned into, or ester could be turned into the, and I ran out of space. Made my cascade a little bit too long. Which also means what? Well, the chloride should be able to turn directly into the ester. Chloride should be able to turn correctly into the acid, and the chloride should be able to turn directly into the amine. Now, what is not going to happen? Well, that's probably not going to happen very easily, right? This is probably not going to happen very easily, right? This is probably not going to happen very easily. So what I need is a key. Now, I'm going to erase this one because it turns out that one will happen, but there's a trick to it. The key is that all of these can be turned into the acid. Right, so I can take the acid chloride and turn it into the acid. I can take the anhydride and turn it into the acid. I can turn the ester and turn it into the acid. I can turn the amide into the acid. The difference is you use acid catalyzed versus base catalyzed, right? So we can all turn in there. And if I had a secret way to turn this into that, right? Would that allow me to turn any one of these into any other one? Yes. Okay. So one of the keys is being able to turn the acid into the top, right? So what we're going to be spending the rest of the day and some of Thursday on is, well, this process, right? How do we interconvert all those? And then also, how do we take some of these to our other functional groups, alcohols, carboxylic, to aldehydes and ketones? Okay, questions? Yes, ma'am. Well, the difference is here we're doing it with acid. Okay, so instead of doing it in a direct nucleophile step, we're going to acidify it. And with acidify it, if you think about it, what we have is not this compared to this, right? But if we use acid, we're dealing with this and that, and it changes the arrow, right? So now we have the ammonium acid. So instead of being a nucleophilic substitution, we're going to change it to an acid substitution, and now we've changed the stability. So we inverted it. Okay, so preparation of acid chlorides from anhydrides. Okay, so the secret to turning the acid into the chloride and having us a whole process to turn any carboxylic acid derivative into any other carboxylic acid derivative is the fact that we can use this SOCl2, so thionyl chloride. The way this works is we have the acid, thionyl chloride is this compound. And then this can come down, kick that off. I'm going to need more room. Then we're going to get proton transfer. Okay, to get me to this position. And then the chloride, which was over here, right? We lost the chloride. Then the chloride can come in and attack the carbonyl. Pi bond break one up. And then electrons coming down, right? We always go through this tetrahedral intermediate. And here's a little different. We get a cascade. Cascade is a fancy way of saying several things occurring at the same time. We get this plus the SO2, and of course it's kind of driven forward by the fact the SO2 is a gas, right? So its entropy is high here, and so the entropy loss. So if we look at this, right, now thinking about that leaving group, is it the OH that's leaving? No. Well, what did we change here? What are we comparing the Cl minus to here? We're comparing the Cl2 minus to the SO2, right? So actually what we've done is all of this is reversible up until that last step. And now the SO2 is gone. This is going to go forward close to quantitative, means close to 100%. And I don't have that driving force between the OH minus and the Cl. What I've done is I've taken the OH minus and I've turned it into this SO2 and the chloride negative. Questions about this one? Okay, well, this then sets up all the other ones, right? Now all we need to know is how do we convert the chloride into other things? And we can do hydrolysis. Right? And water is sufficient here. If we want to look at the mechanism, water comes in, attacks the carbonyl, pi bond breaks, forms our tetrahedral intermediate. We get a proton transfer. Negative charge comes down, kicks off the chloride. Right, a nucleophilic substitution. Alcolysis, right, just breaking it with alcohol instead of water. Okay, so this is a nucleophilic acyl substitution, just has a proton transfer in the middle. Alcolysis, we take the chloride. Again, the chloride's a good leaving group, so we don't need much here but the alcohol. So just take an alcohol. And that alcohol will turn it into the ester. The The way you often see this done is you have some kind of big fancy alcohol, and you see it inverted a little bit, sometimes with pyridine shown. But it's the same reaction, right? It's just where is the alcohol? Instead of taking the chloride and now adding the alcohol, we're taking the alcohol and adding the chloride. Same mechanism as we saw before. Aminolysis, okay, so that's going to be amine breaking. Okay, on this one, we need two equivalents. The other equivalent turns out to be the proton sink, right? So we end up with this as our other byproduct, the salt. I could have done the other ones, the alcohol and the water, with just one equivalent. Usually you do it with an excess, but in the case of the mean, it is important that you have at least two. Questions about these? And again, the mechanism is a nucleophilic acyl substitution. Again, sometimes you see this turned around the other way. In this case, the pyridine is acting as the second base. So here, the important part is that we're turning an amine into an amide. Okay, reductions of acyl chlorides. We'll look at the mechanism on this one. When we do this reduction, we reduce this all the way down to the alcohol. And probably better draw it this way. So we added two hydrogens. So the hydride reacts, right, with the carbonyl, kicks up the pi bond breaks. Now we get this, right? I'm not going to show the aluminum intermediate. Then the oxygen and electrons come down, kick off the chloride. This gives us the aldehyde. But will aldehyde be reduced in lithium aluminum hydride? Yes, right? So then the next step, we get another equivalent of the hydride here, attacking the carbonyl, resulting in this, which coordinates with the aluminum. And then second step, we add our proton source through water to get to a final product. So if we look at it, this was number one, this is two. Okay. Questions about this one? Okay, and this is similar to what we saw before with carboxylic acid, right? We can take carboxylic acid with lithium aluminum hydride, and we can get full reduction to the primary alcohol. So this is going to be similar to our carboxylic acids, right? So we've got carboxylic acid, right? Lithium aluminum hydride going to the primary alcohol. With the acids, it's often hard to stop that, but with the chlorides and the esters, there is a way, and anhydrides, there is a way to stop halfway. And for the reduction to aldehydes, what we need is a special reagent. What we need is a reagent that's more reactive to the chloride than the aldehyde, so that we can react it with the chloride and then it'll stop. It won't react with the aldehyde. Okay, and that reagent for acid chlorides is a lithium aluminum trialkoxyhydride, right? So what that looks like is, instead of having a bunch of hydrogens attached, it's got 3, and this is the T-butyl version. They've got different versions, right? This is what my reagent looks like. So what I'm delivering is only 1 hydride, and then I can be more specific about how I deliver that hydride. Second step is the same. We're going to add water. This reaction is selective to the aldehyde, right? So it can react to the aldehyde. This alkoxy aluminum is less reactive to the aldehyde, and I can stop there. Yes, ma'am. Oh, okay. Yeah, it's lithium, aluminum, and then T-butoxide. So if we look here, right, the T-butoxide, so oxygen and then the TBU, and then 3 of those, and then a hydride. Okay, so other questions about this one? Mechanism is the same. It's just that whenever it gets to the aldehyde, this special reagent is not reactive with the aldehyde, so therefore I can stop, right? So I do the first 2 steps and then it just stops. We can also react acid chlorides with Grignards and other carbon negatives. So we're getting up to carbon negative species. When we have an acid chloride react with Grignards, and you can say 2 equivalents, you can also say excess here, right? But you're going to need minimum 2 equivalents. And I drew that as a 1, but that's supposed to be a 2. I mean, that's supposed to be a 1, not a 2. And then second step, we add our water. So if we think about this reaction, carbon negative reacts here, right? So nucleophile attacks the carbocation, the carbonyl, pi bond breaks. That gives me this intermediate, this tetrahedral intermediate. Now I still have the chloride, right? So that means the oxygen negative is going to come down, kick off the chloride. So chloride's a good leaving group. That reforms my ketone, right? But ketones will react with Grignards. So carbon negative reacts with that Grignard, the carbonyl. Give me this species, right? And then the last step, I add my water to protonate. Now notice what happens when you have Grignards react with acid chlorides. Okay. I'm always going to end up with what type of structure? Well, I'm going to end up with a tertiary alcohol, right? But I'm also going to end up with what? Two of the R groups, right, are the same, because both of those R groups were added with the Grignard. Okay. So here I've got the two methyl groups. If I had added two ethyl groups, it's always going to end up with somewhat of a symmetric group because you're going to be adding two of the same. So when you're looking at retrosynthesis, this is something to watch for, right? Watch for two groups being added. Okay, we're almost to a try this. So one more reaction and then we'll do some practice. Your eyes are getting glazed over. Gilman reagents. A Gilman reagent is made by taking a lithium salt, reacting that with a copper to make a cuprate. If I can spell cuprate correctly. Right, so this is a Gilman reagent. So the Gilman reagent can react with acid chlorides, but it's going to act with the acid chloride in a coupling reaction. Okay. Now the coupling reaction is going to be different than a nucleophile electrophile reaction or a radical reaction or a concerted, like say Diels-Alder reaction where we have a paracyclic reaction, right? So coupling reactions usually have to deal with a metal, in this case, the copper. That copper reacts with two sides, right? It has the methyl already attaches, it reacts with the chloride side, and then it couples those two things together, right? So this is organic chemistry, not inorganic chemistry. So luckily, we're not going to worry about these mechanisms. But the thing that you need to know about them is that they're coupling reactions. So therefore, think about what they're going to do. If you had two train cars, how do you attach the two train cars? You couple them together, right? So what's attached to the Gilman reagent and where the chloride is, we're going to couple those two things together. So if I have a methyl attached to my Gilman, I'm going to substitute or couple where that chloride was, right? So whatever's attached to the Gilman gets coupled to where the chloride is. What happens is the chloride then gets attached to the copper. So we get kind of a switch. The copper takes the chloride, the methyl gets attached to the carbonyl. And this gets us to a ketone, right? And Gilman reagents are kind of like Grignards, right? You're not going to get a lot of wild diversity, but there's diversity. I can do propyls, I can do butyls, I can do some branch groups, right? The R groups can change. I'm just showing methyl here. Okay, so let's try this. What I want you to do is to complete, using your notes, this chart. Okay, so let's take a little time, go back through your notes, and let's complete this reaction sequence for acid chlorides. Oh, forgot one. Go back and look at your notes. If you want to talk to your neighbor, you can. The important part is just find the reagents to complete this chart. Then let's take another 30 seconds. Try to get as many as you can. Okay, let's go ahead and take a look. Okay, so if we start with the acid, I'm going to start with the acid, go to the chloride. We need a special reagent for that. That's SOCl2, right? So that's our dinyl chloride reagent. If we look at the three that I put in purple up here, these are all straight substitutions, right? And do I need any special with a reactive reagent like acid chloride? No. So what did I add to the acid chloride to get to the acid? Well, I added OH, right? I'm substituting OH, right? So is it going to be OH negative or just water? It can be simple, right? Water. Going up to the ester, right? Going up here, what have I added? I've added the methoxide, right? Does it need to go as a methoxide or could it go as an alcohol? It can go as an alcohol, right? This is a reactive species, right? So therefore CH3OH. So when I'm dealing with a reactive group like chloride, I can use straightforward reagents. Going to the NH2, again, kind of looking at what's happening, NH2, I just need what? NH3, okay? I do need how many NH3s? I need two equivalents of that, right? With the methanol and the OH, right, you could assume some excess. With the methanol, with the amine, we need to make sure we have it. The next two I put green. Why did I put them in green? Well, I just picked a color, but why are they the same? They're both what? Reductions, right? They're not just simple nucleophilic substitutions, right? These are both reductions, and I have two different reagents for that, right? For the first one, lithium aluminum hydride, usually shown with excess, right? Second step, water, right? So that's the standard reaction. This would be the same thing would happen with a carboxylic acid. Getting to the aldehyde, now I need a special reaction, right? So I'm stopping. Now I'm going to use the lithium, aluminum, you know, I could put RO3H, right? So you can put the T-butyl, but really it's just alkoxy. I could use methoxide, ethoxide, or the T-butoxide that I showed before. Second step is water. The next two I shown brown. Why did I show them brown? I just picked a color. Why are they the same? What am I making here that's important? All the other ones are transformations, right? Functional group transformations. What about the two in brown? I'm changing the carbon skeleton, right? I'm making carbon-carbon bonds. So the double one over here, which I happen to draw second, that's our Grignard. And I need at least two equivalents, but it's often shown in excess. And then making the ketone, that's where I'm going to use my Gilman reagent. It does have two equivalents of the methyl to the copper. And then followed by water. Okay. Again, remember what we talked about as you go through. It's good to go ahead and do this with all your functional groups. So this is all of our reactions for our chlorides, more or less all the reactions with chlorides you just saw. Okay. Questions about these? Yes. Excess, yeah. Okay. Questions about these? Yes, ma'am. Pyridine? You know, pyridine is not really necessary for the chlorides. Sometimes you'll see it, but it's not always shown. You see it sometimes when you see the alcohol with the acid chloride going to the ester. They show the pyridine. Part of that is that in that case, you don't want your alcohol to be your in excess, right? You want to make sure, because your alcohol is your main group, and I'm just adding the chloride, the carbonyl to it. But in this case, I wouldn't show it because I could add an excess of methanol. So if you don't show the pyridine, I need an excess, right? So when your alcohol is your primary group, they often show the pyridine. Okay. Uh-huh. Yes, ma'am. Well, they're the, you know, the all the substitutions are potentially reversible, but the problem is the chloride's a better leaving group than the methoxide and the hydroxide and the amide. So therefore, they're going in the natural way they're going to go, right? If you look at the reductions, no, they're not reversible. And then, of course, the carbon-carbon bond forming aren't going to be reversible. So potentially the chloride to the alcohol acid, the chloride to the ester, and the chloride to amide is reversible, but I'm going upstream, right? I'm going from a chloride leaving group to an NH2 minus leaving group. I'm not going to do that, right? So therefore, I'd have to do something to reverse it. But theoretically, they're reversible. It's just that the energy is going to the ester, to the amide. Okay. All right, now let's look at anhydrides. So the preparation of anhydrides, you have an industrial process. To make symmetric anhydrides. It also works in the lab, but this is how you get most of your symmetric anhydrides. You take the acid, you heat it up, and you remove water. So in an industrial process, there are materials that will absorb water that you can put in the process, and that's actually going to drive this forward. So you actually remove the water and it drives it forward. In the lab, we do something similar. We distill the water off and we can drive it forward. Okay, but this is only, this two acids plus heat only really works for symmetric, right? You're not going to be able to make unsymmetrical with this. So if you got the diacetate, the dibutanoic, then this will work. The more synthetically useful process is to take the acid chloride and react it with the anion of the acid, right? And I'll go ahead and put that on there so that's a little bit different, right? And in this case, we end up with this, right? And this is a substitution. So, you know, we've got the chloride, we get nucleophilic attack, we break the pi bond, get the negative chloride. Now we've got our carbonyl here. And then, you know, this is somewhat reversible, but it turns out that the chloride is a better leaving group than the anhydride. So then I end up with my anhydride plus the chloride. Right? So the pKa's between those two, right? pKa of the carboxylic acid is around 4.8, but the pKa of HCl negative 7, right? So the chloride's a better leaving group than the hydroxide. Okay, questions about this one? So let's try this. So if you go under the assumption, which isn't a correct assumption, that the chloride and the hydroxide are both great leaving groups, chloride being slightly better than that and the acetate, right? Then what are the reagents here? Do I need anything special to go from the anhydride to the acid? I just need to add what? Water. Going from the anhydride to the ester, what do I need to add? The alcohol. Going from the anhydride to the amine, what do I need to add? The amine. How many equivalents? 2 equivalents. To reduce the anhydride to the alcohol, I need what? I need lithium aluminum hydride and water. Going from the anhydride to the aldehyde, well, I need a special reagent, and luckily it turns out this one works. And I'm using a generic one. Just need a lithium aluminum trialkoxyhydride to do that. Okay, adding 2 carbons. Well, I just need a Grignard. I'm going to need 2 equivalents of that, followed by water. And then to do the coupling reagent, I'm just going to need the Gilman. To go from the acid to the anhydride, I could just use heat, or I could use sodium hydroxide, and I might have to show this one to you, and the acid chloride. And that's pretty small, so let's blow that up. What do you notice about this circle? How close is it to this one? Very close, right? The only difference is the preparation of the anhydride and the preparation of the chloride. So anhydrides and chlorides, same reagent sequence, right? That's because the leaving group properties of the chloride and the leaving group properties of anhydride are similar, right? We got 2 good leaving groups, which means I don't need anything special to hydrolyze these. All I need is water. I don't need anything special to make the ester. I just need the alcohol, right? And all the reagents are about the same, okay? Now, what happens here, right, is that if I take the acid, right, so we're going to focus on that, what happens is that creates this, right, which we saw before, then that reacts, don't need to do that, that reacts with the acid chloride. So all we've done is inverted the reaction process, right? Questions about these? Yes. This one, no, it usually doesn't show it. Usually there's sometimes it'll say a neutral workup, but it's not as essential. The mechanism works to give you the product without the proton, right? If we think about the Grignard, I need that extra proton, so I need to show where it's coming from. So the Gilman gives you the product, then you usually do a neutral workup to separate the product. Where in the case of the Grignard, I add the Grignard, then I'm left with the alkoxide. I need the proton, so I need to demonstrate that the proton's there. Okay. So we got acid chlorides and acid anhydrides. So far you've learned 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, plus another 10. So you learned 20 reactions. Okay. All right. Good. Let's move on into esters real quick. You know what? Let's leave esters for next time. Let's do some try this. So let's try these 3 reactions. Okay, so let's go ahead and take a look at these. Okay, in the first case, I'm turning an amine into an amide. And again, this is a good thing for you to do. Write it down on paper, try it out, write down the words, right? Amine to an amide. I'm going to need to add the carbonyl. I can add it with the chloride. Now I'm going to add pyridine. Why am I going to add pyridine here? Do I want to use 2 equivalents of my starting amine? No, that's my molecule, right? That's the one I've been working on. So therefore I add the pyridine because I need a second equivalent of the amine, nitrogen, right? So I add the amine. Would I always add that? Not if I'm talking about NH3, right? I dump in a bunch of ammonia, right? That's both my equivalents, right? So how we set up these reactions may decide whether we have pyridine or not. Pyridine is the second equivalent of the amine, right? Okay, that's one way to do it. Or I could have had what? I could have used the anhydride, right? And again, because I don't want to use 2 equivalents of my starting material, I'll add pyridine as my second equivalent. Questions about that one? Okay, the next one, we have a Gilman's reaction, right? We've got 1, 2, 3 carbons. Here, 1, 2, 3 carbons. So therefore, I'm just going to couple. So I'm going to draw my molecule, and then I'm going to couple those 3 carbons here. 1, 2, 3. So let's pick a different color. So here's 1, 2, 3. Here is 1, 2, and 3. Okay. So wherever the carbon is attached to the copper, that's where I'm going to attach it to the carbonyl. More or less, I'm just replacing the chloride with that carbon. Okay, and the last one, I'm going to take acid, right, and put 2. Now, if they do this for you, that's a nice hint, but is it necessary? No, it's not necessary. If I just take the acid and I heat it up in the presence of other acid, I could end up with the anhydride. Okay, questions about that one? Let's try a few more. Okay, on the top one, right, we've got the anhydride. I've added pyridine. Why? So I don't have 2 equivalents of my alcohol, right? I just need something to pull off the extra proton. And so here, the thing to think about, what's the important part here? It's going to be the stereochemistry, right? I'm going to make the ester out of this. But the question is about stereochemistry. Is the carbon to oxygen bond, this carbon to oxygen bond, ever part of the mechanism? No, right? The oxygen is attacking the carbonyl, and then I lose the acetate, but I never interfere with this bond here. So therefore I retain my stereochemistry. So if we go back up to our mechanism, oop, didn't show that mechanism. Okay. But if we look here with the alcohol, we're never changing one of the bonds, right? So. The second one, we're doing the reduction to the aldehyde. Can we do this with lithium aluminum hydride? Lithium aluminum hydride would go all the way to what? Primary alcohol, right? So I'm stopping halfway. If I'm stopping halfway, it's kind of like PCC, right? I only wanted to oxidize the aldehyde, not go all the way. I need a special reagent. So if I'm only going to reduce halfway, I need to use the lithium aluminum alkoxy, right? And so I could have isopropyl. So again, it can be many things. T-butyl is very common. The methyl is very common. This one I just put isopropyl, and then second step water, and that's going to stop at the aldehyde. The last one, I'm going to end up with what? Well, this is just hydrolysis, right? I don't need anything else with chlorides and anhydrides than just water. So I'm going to end up with this acid plus this acid. And in most cases, the more complicated acid is the one that you're going to focus on. But in both of these, so if you put the benzene, the benzoic acid, great job. That's probably all the book would want you to do, or I would want you to do. If you put both, that's just showing you understand how the mechanism works.